So let's suppose let's let these be continuous. At some point x equals c. So the following is going to be true. So let's say f of x and g of x are continuous at some point x equals c. Well, then the following combinations of f of x and g of x are also going to be continuous at x equals c. So the sum of f of x and g of x the difference of f of x and g of x, a constant multiple of f of x or g of x. The product of f of x and g of x. The quotient of f of x and g of x provided g of c does not equal 0. So don't get that division by 0. So if you take f of x or g of x and raise them to a positive integer, make a positive integer an exponent or power of f or g, you're still going to get continuity with that combination. Same with roots. Questions about that? So those are the properties we're going to be using. So if you have continuous functions, you can come up with combinations of continuous functions, and those combinations are also going to be continuous. So there's one more dimension, and it's kind of a special one. Composition. So composition of f of x and g of x. So what happens here? Suppose let's say f of x is continuous at x equals c, and f of c is equal to b. Then G composition F is also, oh, one more thing. Skip one more. And let G of x be continuous at f of c is equal to b. Then what we've got, so let me just kind of take a look at it. We've got f of x continuous at x equals c. And then f of c is going to turn into some number b. Now let's suppose g of x is continuous at b. Well, then this means G composition F, which is G of f of x, is continuous at x equal to c. Questions about that? So this allows, or it suggests, one other property. Let's suppose that the limit, introduce this as such, as x approaches c of f of x equals b. So the value of f at b and, I'm sorry, at c, and then f, the limit as x approaches c, are the same thing, but won't be as significant. Then the limit as x goes to c of g of f of x equals g of b, which is going to be the limit as x goes to c of f of x. So in other words, if you're taking the limit of a composition, the limit's going to go inside that g function. Again, you got to make the one caveat and assume g is continuous at f of c is equal to b. We do need g to be continuous. Questions about that? So something that's going to come up, and this is something that they use a lot. It's the intermediate value theorem. It's going to work like this. Let's suppose f is continuous on a closed interval AB. So again, this is where f is continuous on points between A and B. It's going to be right continuous at A, left continuous at B. Let's suppose so draw a picture of what's going on. So we're only focused on f of x between A and B. We're only interested in f of x between those 2 points. And let's say we have some y0 that's between f of b and f of a. Now, f is continuous. So what this means is for every point between A and B, that the limit, as we approach some limit value, we're going to have the limit equal the value of f of x. Let's call this c, where f of c is going to give us y0. Well, it's the intermediate value theorem that says that c exists. That c is going to give you y0. So what does this actually do for us? Well, this is something that's really going to be helpful. Now, let me run through an example. If you're dealing with, for example, equations, and you're trying to find a root for an equation, like we're going to solve for x, say something like this. We're going to have something like this. Well, what can we say about the solution for x? Now, this is not a degree 2 equation, so we can't use the quadratic formula. There are formulas for degree 3 equations, kind of complicated. But is there anything else we can say generally? Well, one thing we can say about this, let's say it's a function. Let's say it's f of x. Well, at this point, we can use those properties of continuous functions. We think about continuity. Again, we're looking for gaps, we're looking for holes, we're looking for infinite oscillations, we're looking for vertical asymptotes. You won't have any of that with x cubed. You won't have that with x. You're not going to have that with the function f of x equals 1. So since this is going to be continuous, with no gaps, no holes, no infinite oscillations, no vertical asymptotes, and this is going to hold true all across the x-axis. It's going to be continuous on the x-axis. Same is true for this, same is true for that. So using our properties, this says we can take combinations, additions and subtractions of these 3 functions, and we're going to get a continuous function. So this says f of x is continuous on negative infinity, infinity, So that being the case, because this is continuous, we can use the intermediate value theorem on it. Perfectly fine. If it's not continuous, we got to be careful because we could have gaps that can make this whole thing go wrong. So how do we do this? Well, what we want to usually try to do is find a number that's above the x-axis and below. Now, what was going to give us a value above the x-axis and below. Okay, what do I mean? We want to find a value for x where x crosses the x-axis, where y equals 0. So let's find some values of x where x is going to be, well, f of x will be bigger than 0. And then a value for x that makes f of x below 0. So you can kind of guess this. You can come up with some numbers, but one number that'll work to get us above the x-axis, or an f of x above the x-axis, let x equal 2. So we're going to get 5. Now, and you might come up with these numbers if you're, say, well, if you're graphing, you're already going to know the answer. So say these are numbers you're just guessing. Let's say we guess x equals 1. So if x is 1, what happens? We get 1 cubed minus 1 minus 1. We're going to get -1. So what does this do for us? Well, we could give a little graph. So roughly speaking, we found 2 points for this function. 1, -1, 2, and 5. Because this thing's continuous, there aren't going to be gaps or jumps that let you jump over the x-axis. You do have to cross through it. So that means somewhere along here, it's got to cross the x-axis. For that function, x cubed minus x minus 1 is equal to 0. So there has to be something between 1 and 2 where this thing crosses the x-axis. So that's how we use the intermediate value theorem. It's actually a pretty helpful thing. And it's going to guarantee, assuming you have a continuous function, again, it can't just suddenly jump up here and keep going. Assuming it's continuous, this point has to exist. So questions about that? So the last thing to mention So what do we do if we have a function that has a discontinuity? Is there a way we can make it continuous? Now, this is going to work if we have a function that has a discontinuity at one point. So, for example, let's say we have something like this. Well, in this case, if we graph it, you can see the problem already. I'm just going to use the graph from the text. at 0, because we're going to have, if x is 0, we're going to get division by 0. We're going to have problems. So for f of x equals sine x over x, well, we've got problems. We're going to have a discontinuity at x is equal to 0. Now, the key thing here, though, this point, the discontinuity is located at 0 and 1. So if we take the limit from either side, the limit as x goes to 0 of f of x equals 1, that's all right. And again, this is the y equals 1. The downfall for us is that the limit, not the limit, I'm sorry. The reason this is discontinuous mathematically is that f of 0 doesn't exist. So that's why we have a discontinuity here. That's why we have this hole. So how can we fix it? Well, what we can do, we can redefine a function, f of x. We'll define one f of x, which is sine x over x when x is not equal to 0. So here we can put those piecewise functions to work. But at the one place where x equals 0, we're going to get capital F of x equal to 1. So this means the limit as x approaches 0 of capital F of x. Well, when x is approaching 0, it's not equal to 0. It's just x at points very close to 0. So this will be the limit as x approaches 0, not equal to 0, sine x over x, and that's equal to 1. And then capital F of 0 is equal to 1. So that means the limit as x approaches 0, capital F of x equals f of 0 is equal to 1. So this says that capital F is continuous at x equals 0. So that's one way we can fix a discontinuity. Questions about that? Let me see here. So that's really it for continuity. The last section in chapter 2, we're going to get into limits that involve infinities. And we're going to get into two types. We're going to be dealing with limits where we actually let x go to infinity, and then we have limits that give us infinite answers. So let's take a look. So limits as x approaches plus or minus infinity. So first off, we want to talk about what infinity is. Infinity is not a number. I'm gonna put an or in there, so it doesn't look like we're dividing infinity. So positive infinity or negative infinity, they're not numbers. One way you can kind of think of them is just keep on going. It's an idea. They're concepts. So what do we do with these? Well, if we say x goes to infinity, what this says is x takes on values that are farther from zero in the positive direction. So as x goes to infinity, x takes on values farther and farther from zero in the positive direction. And you could sometimes see it written as x goes to positive infinity, like we have here. Then x could go to negative infinity. So x takes on values farther and farther from zero in the negative direction. So x going to infinity, x going to negative infinity. So that's what we're talking about with infinity. So kind of a way you can picture it. Your choices for x are just going to get bigger and bigger and bigger and bigger. We'll head out to infinity. And the same for x going to negative. So that's your x going to negative infinity. So what happens in this case, or one or the other? Well, what we're going to do, we're going to start out with what we call one of our canonical functions. And the one we're going to use is 1 over x. And we're going to ask this question, what happens for f of x equals 1 over x as x goes to positive infinity or as x goes to negative infinity? So let's say we have this. So here's 1 over x. Now let's ask this question. As x goes to infinity. So as x gets bigger and bigger, what's going to happen? Well, we see basically that f of x gets closer to the x-axis, or f of x is equal to 0. Now it only gets closer, it doesn't ever actually equal 0, but it's trying to get there. Now let's take a look in the other direction. As x goes to negative infinity, well, f of x gets closer to the x-axis, or f of x is equal to 0. So what this means is this. The limits as x goes to infinity of f of x, well, if we're going to positive infinity, it's 0. And if we're going to negative infinity, well, that's also 0. So how can we use this to good effect? Well, it's going to let us come up with limits, or more complex limits than just 1 over x. And we can use our limit properties to do this. So for example, let's say we have this. Let's say we have 4 over x cubed. Well, in this case, we can think of this as a constant times x cubed, and a constant will pass through the limit. Well, in this case, we can also think of this as 1 over x times itself 3 times. Because 1 cubed is just 1, and x cubed is x cubed. So what we're going to get and we know the limit of 1 over x is as x goes to infinity. And that's going to give us 0. So questions about that? Now, there's a neat application for this that, well, not so much an application, but there's a trick you can use here that's actually kind of clever. And it's how you calculate limits as x goes to infinity, more complicated things. So let's do a couple of these. So let's say we have something like this. Well, what we can do, we can divide top and bottom by the highest power of x. And in this case, it's going to be x cubed. So what that's going to do, we're going to get this. You're going to divide top and bottom by x cubed. So that means you're going to take every single term, divide by x cubed. So 2x cubed divided by x cubed, well, that's just going to be 2. And then 7 divided by x cubed, well, that's 7 over x cubed. X cubed divided by x cubed is 1. Then we have minus x squared divided by x cubed. And then we have x over x cubed. And then 7 over x cubed. So what's going to happen? Let's do some simplification first. But you might see where this is going. So we're going to get something like this. And as x goes to infinity, well, here's 1 over x. Now we know that goes to 0. Something over x cubed, a constant, something over x cubed, again, that's going to go to 0. And really same thing for 1 over x squared. That also goes to 0. So what's going to happen? We'll get 2 plus 0 over 1 minus 0 plus 0 plus 0. So we get 2 over 1 for just 2. So the trick here is divide by the highest power of x, and that's going to see you through. Questions about that? All right. So let me do another one. Let's let x go to negative infinity. So again, what we're going to do, now we can take the limit inside this power. That's perfectly fine. So let's do that first. Now what we're going to do is again divide top and bottom by the highest power of x. It's x squared. So what we do when we get that? So what we're going to get, we'll still have our limit. And then we're going to get, well, x squared divided by x squared is 1. X divided by x squared. And then we have 8x squared divided by x squared is 8. And 3 over x squared. So again, we can simplify. So we get 1. Now again, this is going to be 0. And then we have 8. And this is also going to be 0. All to the 1/3. Or we'll get 1/8. To the 1/3, which is just the cube root. So the cube root of 1/8, what number times itself, in other words, 3 of these numbers multiplied together, what number does this, gives you 1/8? Well, it's 1/2. And that's going to be your answer. So questions about that? So that is sort of an introduction to what these infinite limits are. Let's take a look at the actual definitions. Now, for these, again, like with one-sided limits, you don't seem to be doing much in the homework with these. I'm going to go over at least one example just to get a feel for what it is. But for the infinite limits, we have our definitions. And this is where you get tools to prove that this is actually true. So the limit as x goes to positive infinity of f of x is equal to L if for every, this is that arbitrary epsilon, little tiny number that's just bigger than 0, there exists, it's not going to be delta, it's going to be m greater than 0. Well, no, let me just take that back. Maybe not greater than 0. Let's just m corresponding such that for all x. Now we're going to make some statements about x. Now the key statement, when x is greater than m, then f of x minus the limit, the distance between f of x and the limit is less than epsilon. So, in other words, what's going on here? If we want f of x, kind of close to this limit, then we're going to find some value of x, bigger, located somewhere on the x-axis, where when x is bigger than this location on the x-axis, we call that m, then f of x, the difference between f of x and the limit is less than epsilon. Now, there's a similar definition for negative infinity. I'll go through that one. I'm going to look for a different number. And with n, eventually n is going to be heading off into the negative numbers. We're going to get this, though. We're heading off into the negatives. We're going to be looking at x smaller than n. So when x is smaller than n, then the distance between f of x and the limit is going to be less than that epsilon. Questions about that? So let me do an example with our canonical function. So let me give you a second to copy that down. So let's say we have this. So let's prove the limit as x goes to infinity of 1 over x equals 0. So first thing we got to do is we want to get epsilon greater than 0. Now, we want an m. We're looking for an m where x is greater than m means the distance between 1 over x and 0 is less than epsilon. Now, this is just what we're setting up. We haven't proved anything. We're just stating it. So let's start out. F of x minus L is less than epsilon. So we're going to get 1 over x minus 0 less than some small epsilon we've chosen. Now we're going to search for x greater than m. So let's do that. Now this will be 1 over x less than epsilon. Now we're going to make a little bit of an assumption here. we're going to want an m that's big enough. So we have x greater than 0 when x is greater than m. And this is going to be the case again as x goes to that positive infinity. So what that means, x is not going to be negative. We're going to drop the absolute values. And then you could multiply both sides by x. That would give you 1 is less than epsilon times x. And then divide both sides by epsilon. We'll get 1 over epsilon is less than x. And what we're going to do, we're going to call this m. That's going to be our m. So now that we've found our m, we can say the following. I'm going to make this point first. For any epsilon greater than 0, there exists m equals 1 over epsilon, where x greater than m, then 1 over x, its distance with 0, is less than epsilon. And so that's going to be our answer. Questions about that? So one more note to make. So the limit as x goes to infinity of a constant k is equal to the limit as x goes to negative infinity of a constant k, and that's equal to k. And the way you can see this, as you go out to positive infinity, you go out to negative infinity. Well, f of x is always going to have this constant k value. It's just a little bit more sort of an intuitive thing that can help. All right. So let me do one more example. And this is more of a computational one. It's kind of a tricky one. But let's say we have this. Let me see. Oh, we're running out of time. Let me move on. I'm sorry. I might have to post this one for you later. We're running out of time. So the idea here is, let's see. We do want to mention this. So for horizontal asymptotes, we can give a limit definition of what these are. So y equals b is a horizontal asymptote. For f of x. If, and for this to work, we're going to need a couple limits. The limit as x goes to negative infinity of f of x equals the limit as x goes to infinity of f of x is equal to b. So that's how we know we've got a horizontal asymptote. So, for example, let's say we have this. Now, let's say we take the limit. As x goes to infinity. Now again, let's divide by the highest power of x. And when we do that, we're going to get the following. I'm going to simplify as I go. We'll get 5. This over x squared reduces to 8 over x. And this will be 3 over x squared. Then we'll have 3 plus 2 over x squared. And as we take the limit, this will go to 0, this will go to 0, and that'll go to 0. So we're going to get 5/3. Now let's take the limit as x goes to negative infinity. We're going to use the same technique. So we divide everything by x squared, the highest power of x. So we're going to get the same thing as we did before. The difference is x is going to negative infinity. Well, it's not really going to make a difference. This will go to 0, this will go to 0, and that's going to go to 0. So 5 plus 0 minus 0 over 3 plus 0, or 5/3. And that's going to be our answer. So because the limits as x goes to positive infinity of f of x equals the limit as x goes to negative infinity of f of x is 5/3. Well, this means I'm going to abbreviate horizontal asymptote. That's going to be y equals 5/3. questions about that. So that's one way of working with or stating the horizontal asymptote. It was something that came up in algebra. You ran into this before. This is how you can describe that idea using calculus. So the next thing to look at are oblique asymptotes. Let's see, a little time here. So how does this work? Well, the way you can do it is this. Let's say we have this. X squared minus 3 over 2x minus 4. Now, what we would do in college algebra is we'd do the long division on this. So for the sake of time, I'll just skip it. So what you would actually get is x over 2 plus 1 plus, and then you're going to get a remainder term. So this was the remainder. Now, what we would do is that in college algebra, we would say this would be the oblique asymptote. We would just drop this remainder term. We would kind of give a, as one might call a hand-wavy explanation, which means as x gets bigger and bigger, whether it's in the positive direction or the negative direction, this is going to go to 0. So what we're going to do is this. Note for large values of x, and let me put large in quotes because I'm going to use the negative side of the x-axis. So we might mean numbers that are large in magnitude. X over 2 plus 1 dominates one over 2x minus 4. So how do we illustrate this? Well, with calculus, what we're going to do, we'll take the limit as x goes to infinity of 1 over 2x minus 4. And what's going to happen, this whole thing here is just going to get bigger and bigger. And what we're going to get, and this is sort of a version of the canonical function 1 over x. This is actually a translation of it. Also, different things have some stretching going on as well. But this is going to actually be 0. And the way you can think of it, as x gets bigger and bigger and bigger, if you take 1 and divide it by a bigger and bigger number, I'm going to get a result that's getting closer to 0. Same thing with negative infinity. I get the same thing. So what this means is that for these values of x that are large or negative, large in magnitude, this remainder term goes to 0. That's going to go away. And so for the large values of x, well, large in magnitude, this is going to dominate. So ultimately, as x becomes incredibly negative or incredibly positive, this is what's going to really be describing the behavior of f of x. This is going to get so small, it's going to be practically zero. And so this becomes the oblique asymptote. Questions about that? So let's see. The last thing, how are we doing on time? We got 10 minutes. So what I'll do, I'll mention this. Got one more section on limits that go to infinity. So might have time to start it. Ooh. I don't know if I want to cut things off in the middle of this. So what I think I'm going to do, so we don't just jump into this right away, I'm going to cut off right here. And so what we'll do, we'll leave it like this, and then I'll adjust the homework accordingly. We'll finish 2.6 on Monday, because this is, I think this section is going to take, the last of this section is going to take a little bit of time. We're not going to do it in 10 minutes. So that being the case, I'll leave it like this for now, and then we'll go through this. It's going to be it. So that's it. We're almost done with chapter 2. A little bit more to go. And then we'll finish this up on Monday, and then we'll look at doing an exam review, because we've got to talk about our first exam. And then we'll probably do is start chapter 3, we'll finish 2, start a little bit of chapter 3, do a review on Wednesday, and we'll do the exam the following Monday. So that's it for today. I'll let you go a little early. And other than that, if any questions, let me know.